Thank you.
Praise to Allah, peace and blessings on His Messenger Muhammad and his family. O Allah, ease comes only from you, and you make determination and sadness easy if you wish. Last episode, we detailed key differences, and in this and future episodes, we will delve deeper into differential protection for equipment like line, transformer, and bus bar protection. This episode starts with line differential protection. Stay with us. We will explore differential protection for equipment like line, transformer, and bus bar protection. This episode focuses on line differential protection. Line differential protection is used to protect overhead lines and cables by isolating them instantly during faults. Protection, be with us. Line differential protection protects overhead lines and cables. Protection zones in a power system are defined by CT locations. A protection scheme is a method for protecting equipment. Line protection includes various protections. Higher voltage systems require more complex protection schemes. Protection zone boundaries start and end at CT locations. A protection scheme protects equipment, possibly with multiple systems. Line protection involves various protections, not just line differential protection. It isolates faults, not prevents them. Higher voltage needs more protection. Schemes differ for 11, 30.8, 132, and 400 kV lines. A 3.8 kV cable uses a single bus bar with two CTs, upper for protection, lower for measurement. Protection systems protect the line. Line protection isolates faults timely. More protection for higher voltages. Schemes differ for 11 kV, 30.8 kV, 33 kV versus 132 kV, 400 kV. 3.8 kV cable uses single bus bar with two CTs. Upper CT for protection, lower for measurement. Signal activates overcurrent and earth fault protection, code 5151N. Some stations use instantaneous protection, code 5050N ANSI. The 33 kV protection scheme differs from those for 132 kV or 400 kV lines. For a 3.8 kV underground cable, a single bus bar arrangement with two CTs is used. The upper CT is for protection and the lower for measurement. The protection signal activates overcurrent and earth fault protection, coded 5151N. Some stations also use overcurrent and earth fault protection, coded 5050N. Ideally, the CT is placed before the circuit breaker to avoid the dead zone. However, if space is limited, all CTs are placed after the circuit breaker. The protection signal activates the non-directional overcurrent and earth fault protection, code 5151N. Some stations also use non-directional instantaneous overcurrent and earth fault protection, code 5050N. The best practice is placing the CT before the circuit breaker to avoid the dead zone. However, if the bus bar and circuit breaker are too close, all CTs are placed after the circuit breaker. For different line types, a device is added for automatic reclosing of the circuit breaker after a fault. The best and correct practice is to place the CT before the circuit breaker to eliminate the dead zone between the CT and the circuit breaker. However, in some cases, the distance between the bus bar and the circuit breaker is narrow, making it difficult to add a CT between them, so they are forced to add all the CTs after the circuit breaker. When protecting the same line as before but of a different type, the difference between them lies in the addition of a device that is denoted by a code, which in turn performs an automatic reclosing of the circuit breaker after a fault occurs. The reason for having an auto-closer relay in the overhead line protection scheme and not in the underground cable is that overhead lines are much more exposed to transient faults than underground cables, which are buried underground. It's difficult to access buried cables easily, while overhead lines are susceptible to falling objects or any other incidents that could cause a fault. If a fault occurs on the overhead line, there is a possibility that it could be a transient fault or a permanent fault. Therefore, we use the autocloser to reclose the circuit breaker again to determine the type of fault, whether it is a permanent fault or a momentary one. There is a possibility that this fault could be a transient fault or a permanent fault. Therefore, we use it to reclose the circuit breaker again to determine the type of fault, whether it is a permanent fault or a momentary one. If the circuit breaker closes again, check the type of fault, whether it is a permanent fault or a momentary fault, and certainly the circuit breaker can only be reclosed if the three synchronization conditions are met: voltage, phase, and frequency. Many transient faults disappear simply by momentarily opening the circuit breaker. If the fault is not cleared after opening the circuit breaker and reconnecting it, another attempt, meaning to open and reconnect, will be made before the line goes out of service. Each attempt to reclose the circuit breaker is called a shot. The number of these shots can be selected in the relaying settings. Based on practical experience, it has been found that 80% of faults are cleared after the first opening, 10% after the second opening, while 3% of faults require a third reconnection. While 7% of faults are continuous and still on the line, we need to block the autocloser to prevent the circuit breaker from closing again. If the line is reconnected and the fault persists, this means that the autocloser has successfully done its job by bringing the line back into service. Protections that activate the autocloser are those with instantaneous tripping, like 50 and 50N. For protections with time delay, like 51 and 51N, block the autocloser. Instantaneous protections indicate the fault is on the line, while time delay protections indicate the fault is outside the line or on other equipment. Faults on underground cables are permanent, not transient, as nothing can fall on them. Block the autocloser from the start. Instantaneous protections indicate the fault is on the line, while time delay protections indicate the fault is outside the line or on other equipment. If a fault occurs on an underground cable, it is definitely a permanent fault, and there is no possibility of it being a transient fault because it is not exposed to the risk of anything falling on it. Therefore, there is no need to add an autocloser in the protection scheme for the underground cable. Can you explain the scheme for the cable? If this feeder supplies only one consumer, like a hotel or a hospital, it is called a consumer feeder. In this case, it is preferable to add differential cable protection using a pilot wire if the line is short, up to a maximum of 25 kilometers. However, if it is longer than that, we use fiber optics to communicate between both ends. And of course, fiber optic cables can be used if the line is short. It's also preferable to use a special CT for differential protection, and the intertrip signal is sent between both ends using communication. Usually, it's preferred to use an indication lamp on the switchgear panel to determine whether the circuit breaker tripped due to the local protection or due to remote protection, also known as the intertrip receive signal. This will be very helpful in investigating cases of false tripping. In some cases, a CT supervision relay is added to monitor the CT circuit for any accidental openings by monitoring the voltage rise. If the voltage at the relay terminals increases, it will short the CT secondary circuit after 3 seconds and send a signal to the binary input of the relay to block the differential protection as well. And if the bus bar is of a certain type, a specific protection must be added for it. However, if it is of another type, we can use the same protection for more than one application. For example, we can use it for protection while simultaneously sending to the bus bar no advanced functional protection. So the same protection can be used for more than one application. For example, we can use it for protection while at the same time sending a signal to the bus bar, and at the same time we send to the bus bar Y. Thus, it appears as if the two relays are connected in series, as we cannot divide the current value coming from the CT if we connect them in balance. The trip signal coming from the relay can either go directly to the trip coil to disconnect the circuit breaker or activate 86 lookout relay, which then sends its binary output to the trip coil to disconnect the circuit breaker. In some protection schemes, the trip signal from the relay was sent to both the trip coil and the lockout relay simultaneously. Once the lockout relay is activated, it will send a signal back to the trip coil and also send a circuit breaker close block signal along with a signal to the control center through the SCADA system. Notice in this image taken from 33 kV switchgear with a signal to this is the overcurrent and earth volt relay, and this is the differential relay. This one is the overcurrent lockout relay, and this is the differential lockout relay. This is the bus bar lockout relay. This one is the trip circuit supervision relay, and this is the DC supply supervision relay. Finally, this relay is the auxiliary relay. This is the bus bar lockout relay, and this is the trip circuit supervision relay. This is the DC supply supervision relay, and finally this relay is the auxiliary relay. Nations Renaissance. The purpose of adding the lockout relay is that it happened previously that the high current flow of the circuit breaker turbine coil led to burning the relay output contact connected directly in series with the turbine coil. So the idea of the lockout relay was proposed to be a barrier between the turbine coil and the relay output contact, as the lockout relay is characterized by being a high contact capable of withstanding high turbine coil currents. This idea, though old, was proposed by engineers because old circuit breakers had high tripping coil currents. With modern breakers, tripping coils now draw lower currents, yet engineers have not adapted, adhering to the old way. Another goal is to prevent reclosing after a fault. A reset or mechanism ensures the fault is cleared. It withstands, but engineers stick to tradition. Its goal is to prevent reclosing after faults. A procedure ensures faults are cleared before reclosing. This confirms fault elimination and maintenance, preventing reclosing issues. How can a fault cause reclosing? If it activates a lockout preventing it. The second use is to prevent reclosing. After a fault, whether automatic or manual, a procedure must be followed before reclosing, either through a manual reset or a mechanism ensuring the fault is cleared. This ensures protection engineers confirm fault elimination and perform necessary maintenance, avoiding issues with reclosing the circuit breaker. A fault can trigger the circuit breaker to reclose automatically while activating the lockout that prevents it from closing again. The autocloser wants to reclose the circuit breaker while the lockout prevents it. Therefore, design engineers decided not to use the lockout relay if the autocloser relay is used. Ensure no issues with reclosing the circuit breaker through maintenance. Faults may cause automatic reclosing despite lockout disconnection. How do these actions coexist? Autocloser recloses, lockout prevents. This conflict is found in stations. Engineers avoid using lockout with autocloser. They use ANSI 94 tripping relay. 86 lockout needs manual reset. 94 tripping resets automatically. The autocloser tries to reclose the circuit breaker, but the lockout stops it, causing conflict. Engineers decided not to use the lockout relay with the autocloser. They introduced the 94 tripping relay, which is self-resetting and doesn't conflict with the autocloser. Unlike the 86 lockout relay, which needs manual reset, the 94 tripping relay resets automatically. Thus, a circuit breaker close block can only be done with the 86 lockout relay, not the 94 tripping relay. Another relay was placed instead called the tripping relay, which is designated according to the ANSI device code as 94. The difference between the 86 lockout relay and the 94 tripping relay is that the 86 lockout relay requires a manual reset to operate, while the 94 tripping relay is self-resetting, meaning it resets automatically and electrically without any external intervention. This makes its operation not conflict with the operation of the ultra-closer relay. This means that we can implement a circuit breaker close block using the 86 lockout relay only, and we cannot do this using the 94 tripping relay because it is self-resetting. This ensures that its operation does not conflict with the operation of the ultra-closer relay. This means that we can implement a circuit breaker close block using only the 86 lockout relay, and we cannot do this using the 94 tripping relay because it is self-resetting, only 36. We cannot do it using because in summary, if we have a situation where we definitely need to use protection that activates instantaneously, then we will take a signal from it to perform an action. As for the 86 lockout relay, it will be activated by the delay deprotection. If the lockout relay is activated, we will take its output contact and send it to the binary input of the autocloser to create a block for it. We want to point out that in some stations, the lockout is being used as if it were a function within the relay itself without being used as a standalone relay. This function performs the exact same role as the lockout relay, and it can be reset by pressing this push button, especially for the protection scheme for 33 kV lines. We will take it from him and send it to the person who is responsible for his work, and we want to inform him, in some stations the lockout is being used. This function acts like the lockout relay and resets with this button. Sometimes a voltage transformer is used for 21 distance and 67N earth volt protection. The same scheme applies to 30.8 kV lines, but sometimes a voltage transformer is used for 21 distance and 67N earth volt protection. In motor protection, current and voltage, calculate fault distance, zip, Parker, VI, voltages, determine fault current direction, forward or reverse. Modern stations now have separate protections, unlike before. The voltage V is taken from the system and the current I is taken from the fault. The voltages are used as a reference to determine the direction of the fault current, whether it is forward voltage or reverse voltage, meaning whether it is a forward fault or a reverse fault. Recently, in some modern power stations, there has been an addition for each one separately, unlike before when it was only for the bus bar and incoming lines. The renaissance of a nation, indeed. In high voltage stations, we use the bubble bus bar single circuit breaker, and a CT is for main protection, including line differential protection, distance protection, and directional airflow protection. A CT is also for backup protection, including overcurrent and airflow protection. The location of the protection CTs is before the circuit breaker to eliminate the dead zone. As mentioned, I have backup protection with overcurrent and airflow protection. CTs are before the circuit breaker to eliminate the dead zone. Bus bar protection CTs are after. Circuit breaker remove dead zone. CTs after select breaker overlap line protection. CTs for bus bar protection follow the select breaker for overlap with line protection. The difference between discrimination and check zones will be discussed in the differential protection episode for the bus bar. Usually a device operates, sending signals to another. Devices like 7L21 in zone 1 and 67N send trip signals to trip coil 1, while the other acts as a backup. Devices 7L, 21, 67N, trip coil 1, backups, trip coil. One operates from the trip signal, sending a signal to trip coil 1. The other acts as a backup, sending a signal to trip coil 2. In some schemes, each lockout sends a signal to both coils. Lockouts activate the circuit breaker to fail, starting a count if it doesn't open, and send an intertrip signal. It sends the trip signal to trip coil 2. In some protection schemes, each lockout sends a trip signal to both trip coil 1 and trip coil 2. Notice that all the lockouts activate the circuit breaker to fail, so it starts counting if the circuit breaker does not open. At the same time, it sends an intertrip signal through communication to disconnect the remote end circuit breaker. In some other high voltage stations, there are two main protection relays, and they are usually from different manufacturers. Each main relay has its own RCT, and each relay takes its voltage readings from a different VT secondary winding. These two main relays are for protecting the same equipment, so for a single line protection, there are two main relays, each from a different manufacturer. The same applies to transformer protection and bus bar protection. We cannot say that one relay is the main and the other is the backup. Both are main, meaning that they both perform the primary protection independently. The first relay is usually denoted by the symbol FBFM, which stands for Feeder Protection First Main, and the second relay is also denoted by the symbol FBFM. It is an abbreviation. In the past, the protections used in main 1 were different, while the protections used in main 2 were different as well. However, in modern stations, all protections have been standardized, meaning that the protections for main 1 are exactly the same as those for main 2, and the protections, each one are exactly the same. Are the protections the same? The two main protection relays can be placed in one protection panel, or each main protection relay can be placed in its own independent panel. It is preferable for each panel to have its own DC source. This diagram illustrates the possible distribution of currents and voltages to the relays, the distribution of the DC sources to each panel, and how to send the output contact to the trip coil, which in turn disconnects the circuit breaker, relies heavily on the voltage level, the importance of the equipment, and the available cost. The most reliable option is the fourth one, while the least reliable is the first option. In some 132 kV overhead line circuits, the circuit starts at the end of the SF6 circuit breaker with a section of underground cable until it meets the towers supporting the overhead line. This part is called name, and this section is protected only from the beginning of the cable by using differential protection on the cable. This differential protection is fed from the current transformers at the beginning and end of the cable. We don't want to leave in your mind this is specific only to certain applications. In one of the oil stations, this system was used, and at the same time, the same system was used with the 400 kV. This means that the importance of the equipment to be used is the most crucial factor in choosing the required reliability level, because surely anyone who wants to invest in oil, it won't matter to him what we lack. High voltage stations have bus bar methods like 133 kV stations, commonly using the 1.5 circuit breaker. This setup includes 3 breakers for every 2B, arranged in either an H or I configuration. Both configurations achieve the same purpose, only the drawing method differs. 1.5 is circuit breaker. The 1.5 circuit breaker setup includes 3 circuit breakers for every 2B, and the distribution of these breakers can either be in an H configuration or an I configuration. Each configuration represents a 1.5 circuit breaker arrangement and achieves the same purpose and goal, but the only difference is in the drawing method. The type used varies by group across protections. The first type, name, has multiple name. The red CT is for primary protection, the blue CT for secondary main protection, and the green CT for busbar protection. If circuit breaker 52.1 is open with 1000 amps from P1 and 500 amps from P2 distributed 1500 to 1 is shown, the vector sum of currents will be 1 amp. The blue CT is for the same P as the secondary main protection, while the green CT is for busbar protection. If the circuit breaker 52.1 is open and the current drawn from P1 is 1000 amps while the current drawn from P2 is 500 amps, it was distributed 1500 to 1 as shown in this diagram, and thus the vector sum of the currents will be 1 amp, and it will also be 1 amp. The 1 amp going to P1 from this is the result of the vector sum of 0 plus 1. This CT has an output of 0, meaning there is no current at all because no current has passed through the primary current since the circuit breaker 52.1 is open. And indeed on his house from Lily will be 1 amber too. The 1 amp going to P1 is 0 plus 1. This CT has an output of 0, indicating no current as the circuit breaker 52.1 is open. This CT converts 1000 amps to 1 amp for the relay. 1 amp to P2 relays is from 3 amps and 2 amps. As for the CT, it passed 1000 amps on the primary side and it converts from 1000 to 1. So it converts the 1000 amps to 1 amp going to the relay. The 1 amp going to the P2 main relays is the result of the vector sum of 3 amps and 2 amps, or just now, it results from the vector sum of 3 amps and 2 amps. 3 minus 2 equals 1. And the 3 amps came from this CT, which has a CT ratio of 500 to 1, and it passed a current of 1500 amps. As for the 2 amps, they come from this CT, which also has a CT ratio of 500 to 1, and the current passing through it is 1000 amps. So we had 1500 amps coming from here, which went to B2 or transformer B2 with 500 amps, leaving 1000 amps entering the 500 to 1. Now if the tie circuit breaker 52.2 is open, the current from P1 is 1000 amps and from P2 is 500 amps. Currents on P1 and P2 are 1 amp each. The 1 amp to the P1 main relay results from 1000 amps passing through with CB52.1 closed, allowing flow to line P1. For the second, it's 0 because no current passes through with the tie CB open, resulting in 0 secondary current. The 1 amp to P2 is from 500 amps converted by the CT. The other CT gives 0 current as the tie CB is open. Therefore, only the current from the 500 to 1 CT is present. If CB52.3 for bus 2 is open and current from each P remains, the current on P1 stays at 1 amp. The second is 0 as no current passes. The circuit breaker or tie circuit breaker is open, resulting in 0 current. 1 amp to P2 from 500 amps CT conversion. The other CT also gave 0 current as the tie circuit breaker is open. Thus, only 500 to 1 CT current is present. If breaker 52.3 for bus 2 is open and each P's current remains, vector sum on P1 and P2 stays 1 amp a des. 1 amp to P1 from 1.5 amps minus 0.5 amps, with 1.5 amps from 1500 amps through CT, 1000 to 1 ratio. So I only have 1 current coming from the 500 to 1 in this CT. Now if the circuit breaker 52 to 3 for bus 2 is open and the current drawn from each P remains the same, then the vector sum of the currents on P1 from the relay will remain as it is, which is 1 amp, and on P2 from the relay it will also remain as it is, which is 1 amp. As for the 1 amp going to P1 from the relay, it results from 1.5 amps minus 0.5 amps, and the 1.5 amps is due to a current of 1500 amps passing through this CT, which has a CT ratio of 1000 to 1. And on P2 from the relays, it will remain the same, which is also 1 amp. As for the 1 amp going to P1 from the relays, it results from 1.5 amps minus 0.5 amps, and the 1.5 amps come from a current of 1500 amps passing through this CT, which has a CT ratio of 1000 to 1. Sprinkle him with 2000 and 1001. So every 1000 amps will give me 1 amp, and therefore 1500 will give me 1.5 amps on the secondary side. This 1500 amps on the primary side will send 1000 amps to line B1, leaving 500 amps passing through this CT, which has a CT ratio of 1000 to 1. So every 1000 amps will give me 1 amp, and thus 500 amps will give me 0.5 amps. The 1 amp going to P2 from the relays is the vector sum of 1 amp plus 0. Here the current value is 0, as no current has passed through it since the circuit breaker is open. This CT has passed a current of 500 amps. the CT converts from 500 to 1 amp and sends it to B2. If all 3 circuit breakers are closed and the current drawn from each B stays the same, the total 1500 amps will be divided into 2 equal parts. The vector sum of the currents on P1 main relays stays at 1 amp, and on P2 main relays it also stays at 1 amp. Current entering relay stays constant whether circuit breakers are open or closed. The second type of stations are name. A protection is placed before and after. The third type is name. A group is placed on the line or before its exit. The total 1500 amps will be divided into 2 equal parts, with each part coming from a different bus bar. The vector sum of the currents on P1 main relays will remain the same at 1 amp, and on P2 main relays it will also remain the same at 1 amp. This leads us to conclude that value of the current entering the relay will remain constant regardless of whether the circuit breakers are open or closed. The second type of stations is name. The third type is the 5 CTs method, with CTs placed on the line or before exit. And after the tie circuit breaker, balance B1 and B2 protection. 5 CTs method, with CTs on the line or before exit. Red CTs are parallel for 87 TD primary protection, an inverted T area, the T connection. Blue CTs are parallel for 87 secondary protection. Green CT is for 87 bus. Red CTs are parallel for 87 TD primary protection, an inverted T area, the T connection. 3 blue CTs are parallel secondary protection for 87. The green CT is for 87 bus bars, using 1 CT per main protection on the line or bus, down meaning on down, a down fault. The 6 CTs method in high voltage stations involves 2 CTs feeding main protection groups, distributed for overlapping bus bar protections, P1 and P2. In this case, we use only 1 CT for each main protection for the bus, which is the CT located on the line, for its exit, or the CT located on the bus itself. As for the fourth type of distribution method for CT groups in extra high voltage stations, it is called the 6 CTs method, and there are several configurations for this type, where the 2 CTs feed the main protection groups for each device, and these CTs are distributed before and after the tie circuit breaker to achieve overlapping between the protections of bus bars P1 and P2. The distribution method of the CTs for these protections can be analyzed from this visible diagram, and it can give you some time to reflect on it. We distinguished each protection with its own color so that you can differentiate or tell them apart. It's also worth mentioning that the way to connect the 2 CTs to the relay can be done by connecting them in parallel before entering the relay, as shown in this image, or by introducing each CT separately into the relay, as shown in this image, and then performing a vector sum of both currents within the relay configuration. And existence. Connecting 2 CTs to the relay doesn't mean testing it twice with different CTs. We test with 1 CT, then measure each separately. Quick tests ensure the relay works with all CTs, and the configuration file is correct. The final method uses 6 CTs, placed before and after the tie circuit breaker, and on the line before its exit. There's no harm in taking quick test shots to ensure that the relay works with all the CTs and that the configuration file is correct. The final form of the distribution method is the 6 CTs method, where the CTs are placed before and after the tie circuit breaker, in addition to having CTs installed on the line itself before its exit. The diagram shows 380 kV overhead line protection devices. There are 2 main protection groups fed by CT3 Core 1 and CT3 Core 2. Each main protection is fed from only 1 CT, unlike before with 2 CTs. Each device should be from different manufacturers to prevent faults. There are 2 groups of differential protection for the T circuit, with each group fed from 3 CTs, and 2 groups of differential protection for bus bar 1A, and 2 groups for bus bar 1B, with each group fed from only 1 CT. We explained the line protection scheme for the overhead line and the underground cable. As we said before, each device must be manufactured by a different factory to prevent specific faults in the device components. We also have 2 sets of differential protection to protect the T circuit. Each set is fed by 3 CTs. We also have 2 groups of differential protection for bus bar 1A, in addition to 2 groups for bus bar 1B, with each group fed from only 1 CT. In this episode, we explained the line protection scheme for the overhead line and the underground cable, and we distinguished between the protection methods for each type. Then we moved on to the protection methods for different voltage levels: medium voltage, high voltage, and extra high voltage. Stay tuned for the next episode, where we will discuss the details of line differential communication between each pair of devices. With that, we conclude and thank God, the Lord of the worlds. We hope to see you again soon.